Let's talk about testing the slope parameter beta 1 in simple linear regression. I'll use the skin cancer mortality and latitude example. And first of all, let's take a look at a fitted line plot. We have mortality on the vertical axis, latitude on the horizontal axis. Here's our fitted regression line, and here's the equation of the line. And so just kind of a visual impression of the data and the regression line is that there seems to be a fairly strong negative linear relationship between mortality and latitude. But let's test that with a formal t-test. So to do that, I'm going to fit the model again, but this time I'll use fit regression model. And I'm going to look at the coefficients table. So this table here. So there's two rows in the coefficients table. There's one corresponding to beta 0, which Minitab just labels constant. And then the second row is for the predictor latitude. So this is the one that we're interested in. This relates to beta 1, the slope. The first column gives us the coefficient estimates. So minus 5.978 is our estimate of beta 1. That's this number here. The next column is the standard error of that estimate. So standard error of the slope estimate is 0.598. And key statistic for testing the slope parameter is the ratio of the coefficient and the standard error of the coefficient. So the formula, it looks like this. B1 is our coefficient estimate. That's our estimate of beta 1. And then SE of B1 is our standard error of our coefficient estimate. And in the formula here, in the numerator, we're subtracting beta. So what does that mean? Well, that means we're setting up our null hypothesis as beta 1 equals some number beta. And our alternative hypothesis is that beta 1 is not equal to that number. Typically, the number we're most interested in is 0 for the slope. So if beta is 0 in this formula, this part just goes away, and we have B1 divided by SE of B1. So that's what this column in the coefficient table is. It's the t-statistic for testing whether the parameter is 0. And the reason that 0 is an interesting number is because imagine if the slope was 0, our regression line would just be a flat line, and there'd be no real evidence of a linear relationship between y and x if the regression line was just flat. We had just a random scatter of points. In this case, we got minus 9.99 for our test statistic. So minus 5.978 divided by 0.598 comes to minus 9.99. Under our null hypothesis, the t-statistic has a t-distribution with degrees of freedom equal to the sample size minus 2. Sample size in this case is 49. And so 49 minus 2 is 47. So our test statistic under the null hypothesis has a t-distribution with 47 degrees of freedom. To make our decision we can calculate a p-value. And the way we set this test up was as a two-tail test. The alternative hypothesis is that beta 1 is not equal to 0. So our rejection region is going to be in both tails. And the p-value is the sum of the tail area to the left of minus 9.99 plus the tail area to the right of plus 9.99. 9.99 is way out in the tail of a t-distribution with 47 degrees of freedom. So those tail areas add up to, Minitab is telling us 0.000 to 3 decimal places. And then finally, we make our decision by comparing that p-value with the significance level of the test. Let's suppose that our significance level is 0.05, which is the usual significance level used in tests of this nature. Because the p-value 0.000 is less than the significance level, 0.05, we reject the null hypothesis in favor of the alternative. So that means there's sufficient evidence at the 0.05 significance level to conclude that there is a linear relationship in the population between our predictor latitude and our response mortality, skin cancer mortality. And that kind of confirms what seemed to be evident from our graph. So there's a few more things to note about this t-test for the slope. So one is that we considered a two-tail test because we had not equals in our alternative hypothesis. We might have, before we even looked at this data set, we might have speculated that as latitude increases, so the further north we get in the country, then mortality from skin cancer would tend to go down. So if that was the case, then we might be more interested in doing a lower tail test in this context. Then in our alternative hypothesis, we would have beta 1 less than 0. And our test statistic will be exactly the same, minus 9.99. But now our p-value would just be the tail area to the left of minus 9.99. We wouldn't add on the right-hand tail area to the right of plus 9.99. We're only interested in the left tail when we're doing a lower tail test. In this case, it doesn't really make any difference because Minitab is telling us that the two-tail p-value is 0.000, so the one-tail p-value is half of that, so it's still essentially 0. In other examples, we might want to do an upper tail test, then we would have a greater than 0 in the alternative hypothesis, and then our p-value would be the tail area to the right of the test statistic. And then one last thing to note is there's actually another way of doing this test, this two-tail test for the slope in simple linear regression, and that's with an f-test rather than a t-test. And the f-test is covered in the analysis of variance table. And we'll talk about the analysis of variance table in more detail in another video. But just briefly, there's an F statistic here, 99.8, and this F statistic is the square of the T statistic for the slope, minus 9.99. Let me just demonstrate that to you. So let's square the T statistic, so minus 9.99. If I square that, I get 99.8, and that's the same as the F statistic in the analysis of variance table. And there's a relationship between an F statistic with 1 numerator degree of freedom and 47 denominator degrees of freedom, and a t distribution with 47 degrees of freedom. The F distribution is the square of the t distribution. And so these p-values, this one here in the analysis of variance table, and the slope p-value in the coefficients table, these are exactly the same. It's a little hard to tell in this example because they're both 0 to 3 decimal places, but you'll see in other examples that these two numbers are always exactly the same, this one here and the one in the analysis of variance table here. So those are some things to take account of when you're doing a test for a hypothesis test for the slope parameter beta 1 in simple linear regression.